Okay, let's do this. We've got an argument here. We got premises. A or C implies D, not B, and A or B. We want to prove that this argument with conclusion D is valid, but we don't want to do it in an informal sense. We don't want to use English sentences. No, 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 no. We want to use formal reasoning. This means we want to use mathematics to say something about English, to say something about the nature of our reasoning. We're going to use mathematics. Here we go. Here are our premises. Remember, when we work these proofs, we number the individual lines so that we can refer back to them at later steps. P stands for premise. We put down the three things that we know are true, and then we try to generate a sequence of statements, each one precisely justified by one of our rules of inference and referring back to previous statements in our proof. So let's take a look at this, for example. What are we looking at? We want to be able to show that D is true. We know that A or B is true, and we know that B is not true. So that means A's got to be true, right? And if A is true, then A or C, okay, that implies D, like A or C is true, right? This isn't hard to see. But it's hard to specify precisely why it is valid. If you just would structure this to someone and talk to them about it, it would be clear to them. Oh yeah, okay, sure. But they wouldn't be able to say why. We can say why. Formal reasoning allows us to specify with more precision than you knew existed what exactly it is that we're doing when we think. We have some rules already that we know about. Remember modus ponens? It says that if I know that if A then B is true, and A is true, then I can conclude that B is true. We used this a while back. This is a new way to view it. This notation here means that what is on top of the bar, these are the things that we know. And what's on the bottom of the bar, this is what we can conclude. So this says that we know these two statements are true. We can conclude B. Modus ponens doesn't help us yet. We will use it here to declare to conclude that D is true, right? Once we get that A or C is true, then we'll get D using modus ponens, but we don't have that yet. We don't have a line in our proof that says A or C is true, and we cannot use modus ponens until we get that. Modus tollens. This is another one of the proof rules that we've learned already. We know that if we have A implies B and then we negate the consequent, we negate the antecedent. We know about this, but again, that doesn't apply in this situation either. What we need is a rule that says if I have A or B, then, I mean, come on. I know that, and I know that B is false, then come on, I know that A is true. We have that. It's called disjunctive syllogism, another band name. Here, it says that if I have A or B and I have not B, then I can conclude A, or the other way around. So I'm going to write down that A is true formally because I can prove it using my rule of inference. I have to justify every single line in this sequence of statements. That's what makes it a formal proof. Every line is justified with reference to a proof rule, with reference to a rule of inference that makes up our logical system. If you have a different collection of rules of inference, you will have a different logical system. You can have a proof that is valid in one system and invalid in another. So then the discussion becomes which set of proof rules is best or is true. Okay, where are we at now? Now we want A or C to be true, right? Well, A is true, so of course A or anything is true, right? But we don't have a rule for that. We need another one. This one is called addition. It says if I have A, I can build up. I can build up using the or. So A or B is true if A is true. Remember, I told you to think of or like addition. The name of the rule, it's addition. We just add to it. So we'll call on addition with line number 4 to give us that A or C is true. And now we use modus ponens with 1 and 5 to give us D. Q, E, D. There we go. This is a formal proof for the validity of this argument. Let's do another one. Now we want to show that we've got these premises and this conclusion. We want to show that the conclusion now is B and C. So we're going to be able to get to that. So in this case, we have not A, and we have A or B. So we use our disjunctive syllogism to give us B. And now we can use modus ponens to get us C using lines 3 and 4. We always have to note exactly which lines we're dealing with. It's of critical importance. Now we need, in order to conclude that B and C is true. So we've got B here on this line, we've got C on this line, but I need to know that B and C together is true. It looks obvious, right? But no, we can't just say obvious. We can't just write it is clear that. We have to specifically have a rule that lets us build this up. It's just the definition of and. So it's called conjunction. This is what and is. This is equivalent to the truth table, right? When we build that truth table and put those logical equivalencies together, and we do all those algebra problems, that's basically what we're doing here. But this is a different framework. This is showing formally that something is true. This isn't crunching the numbers and pushing the symbols around. I know I mixed them a little bit on the one video, but this is a fundamentally different thing. So I call on the conjunction, and I conclude that B and C is true. Let's take something that's written out in English. If either algebra is required or geometry is required, then all students will study mathematics. Algebra is required and trigonometry is required, therefore all students will study mathematics. Here are the premises. If algebra or geometry, then study math, and we know that algebra and trigonometry is true. Now the careful viewer might go back and say, wait a second, didn't you go on a rant about how this inclusive or doesn't apply in English? Well, English isn't a formal language. It's going to be inclusive sometimes, right? Right here, the inclusive or is a fine way to characterize this, even though it has either, right? Like it just depends on the context. Here, the inclusive or is just fine. We need a new rule though, because I want to say that A is true. I've got that A and T is true, right? But I don't care about trigonometry. Right? Trigonometry is not part of what I'm trying to get at. I want to conclude M, and T isn't part of this at all. So T is just an outlier. I don't care. I want to know that A is true, and I know that A and T are true. So I mean, of course, A is true. Everything in an and has to be true if the whole thing is true. But I need a rule to say that. So simplification is basically the opposite of the addition rule. Simplification says, here I've got these things, I'm going to just reduce. Addition says I can build up with or. Simplification says if I have this, I can reduce. So I'm going to call in the simplification rule here. But now I have to build up. So I call on addition, so I can build up A or G. And then I've got modus ponens. And I'm done. Right? This is it. Right? If you would just show this to someone who's of reasonable intelligence, but is not technically minded, and you say, is this reasonable? Right? Don't even say, is it valid? That word, they don't know what that word means. Is this reasonable? Is this a logical thing? They read it a little bit, and then yeah, they'd say, of course. But then you ask them, why is it? And you think they're going to say something about modus ponens and simplification and formal logic? No, they're not. They're going to say, because. And they're going to have a hard time articulating anything beyond that. Even a very intelligent person, right? It's just that not something people think about. People don't think about their own thinks. People don't think about reasoning in this way. Unless you happen to find a philosopher or a mathematical logician, most people, even really intelligent people, they're not reflecting on this. And that's what we're doing in this entire course. We're showing that this mathematics can be brought to bear on something that prior to it, we didn't even think was possible to think about. We're going to do this same thing with computation itself. We are computer scientists. And what we do is compute. But what does that mean? If you're not sure what the answer to that is, it's the same thing as the intelligent person not understanding what you mean when you say, why, indeed, is this argument true? Why is this argument valid? Why does it make sense? Why would you consider this a reasonable or logical thing to say, right? You'd have to show them all of this. You'd have to say, okay, well, I need a rule here to allow me to conclude A and then conclude A or G, and then you got modus ponens, right? This is hard, right? There's a lot to explain here. There's not a whole lot to explain here. This English is informal. This is informal reasoning right here. This is what the vast majority of reasoning is. It's written out informally. There's a certain relationship between the formal and the informal. But most people are here in the informal. And they can't justify why their informal conclusions seem reasonable to them. It's just because that's how logic works. Or maybe they can come up with something. If it's invalid, maybe they can actually manufacture a counterexample, which would correspond to a line in our truth table that would indicate F. But if it's valid, they're not going to go through all possible combinations. That's not how people think. The big takeaway from all this is not that you become an expert at generating these proofs so that you can go work as a software developer and sit down and spend the first half of your day writing formal logic proofs. The point of this is so that you understand what it is that we as humans have to say about something that before you considered this, you didn't think it was possible to have things to say about. Because we're going to do the exact same thing for computation itself. Let's review all of our rules of inference. Modus ponens, modus tollens, disjunctive syllogism, simplification, conjugation, conjunction, and addition. There are some more, right? So here's double negation. If we ever need this is useful. If you have not A, you can conclude A. If you have A, you can conclude not A. This will come in handy. Contradiction. If I have A and not A, I can conclude false. Hypothetical syllogism. We mentioned this one before. If I've got a chain of implications, I can drop the middle term out. Constructive dilemma. If I have A or B, and then A implies C, B implies D, I can conclude that either C or D is going to happen because I know one of these two happens, and so if you just look at this, you'll say, of course. But you have to prove it, right? These two, hypothetical syllogism and constructive dilemma, these are provable from these other things. So they don't necessarily have to be part of your most basic list. The mathematicians oftentimes like to come up with the most basic, most minimal list of things in any set that they're concerned with. So these might not necessarily be listed, but we might as well. We're going to use them. These are very useful theorems. So we could prove them as a theorem and then use them, or we could just say, okay, this is really nice to do. So here's conditional proof. We're going to have a whole video on this one. This one is really complicated. This is how we prove conditionals are true. And I've mentioned before, conditionals are tricky because they don't have anything to do with A and B. If I prove that A implies B is true, that says nothing about the truth value of A or B. It just says that if A happens to be true, then B is true. Doing these proofs sometimes creates a situation where we are introducing new premises to the proof, and we're doing something called a subproof. We'll get to that. We've got several videos on formal proofs here. This is just the very basic introduction one. And then we have indirect proof as well. Indirect proof is proof by contradiction, if you're familiar with that from your mathematics course. From not A, derive false. These derives in here, this means that you start off and you have a premise. You've got some line in your proof that has either A or not A on it. And then from that line, you're able to draw a chain of reasoning that concludes with false, say, for indirect proof. And then you're able to conclude that A is true. So you start off with a contradiction. You start off by assuming that not A is true. And if you get something that's false, then you can conclude that A is true. These are our proof rules. These are our rules of inference. This is the beginning of our study of formal reasoning.